And thank you, Mr. Dinesh, actually, for inviting me to deliver this lecture. And I should really thank him because he has been pursuing me for quite a long time. For maybe for 2, 3 months, he has been asking me to deliver this lecture. I've been somehow actually I was just avoiding it, but somehow he caught me that you have to deliver it. So it's good actually that I'm able to share my knowledge here. And I want to give some disclaimers here. First of all, in the beginning itself, uh, I'm audible to all the people.
Yes, sir.
Okay. Okay. I want to give some disclaimer that EGS NRC cannot be learned in a single session, like 1 hour session. So I will try to cover some physics part, some actually stochastic process part, and then also some codes, few basic codes of EGS NRC. I will try to share it here, and of course the other advanced topic like beam NRC, XYZ NRC, all these things can be delivered in a future lectures if time permits. Okay, so today I'll be delivering a very basics of Monte Carlo simulation processes. So let me begin by saying that uh, we know that because we are all physicists, we know that we have a deterministic quantities and we have stochastic quantities. Like we have a dose, which is a deterministic quantity, but whereas the interaction process is a stochastic quantity. It means that we can't decide which interaction takes place at any point of time inside the material when the radiation interacts with the material. So it means it's a stochastic process. So Monte Carlo simplifies, and it's basically a stochastic method for estimating deterministic quantities that are difficult or impossible to compute exactly or analytically, because we can't decide that which process takes place. So we have to use a certain sort of the probabilistic methods so that we can decide what quantity actually what exactly happening inside the material. The Monte Carlo methods are a broad class of computational algorithms that rely on repeated random sampling to obtain numerical results. I highlighted certain points here because I'm going to deal with this individually. We are going to do a random sampling. In a probabilistic method, is always sampling is a term used because we want to take out some samples from that and do that one so that I can find out, I can or estimate the deterministic quantity. So we have to do something with the random sampling methods and numerical results also. They are often used in physical and mathematical problems and are most useful when it is difficult or impossible to obtain a closed form expression. Suppose we have any mathematical expression, we can easily estimate it. But when we are not able to get a closed form expressions, then it has to be determined by only stochastic methods. So in Monte Carlo simulation, outcomes are sampled from a probability distribution. It can be used. Like example, whenever we talk about probability, something that comes in our mind is a dice roll or a coin toss. That's what normally comes to our mind. So we are tossing a coin. We know that once I toss a coin, I get either head or tail. But a number of turns I toss it, then I can estimate what will be the final result of that. The same way with the dice roll also. The same method can be used to find out which interaction will a photon undergo when it interacts. It can be used to sample from a continuous probability distribution also. That was a discrete probability because like we know that interaction is a discrete probability, whereas in a Compton process, like example, in Compton interaction takes place, what will be the scattered photon energy will be there and which direction it will go. That is the continuous probability. So that has to be done. So we can use MC Monte Carlo for both discrete probability as well as the continuous probability also. So the general applications of Monte Carlo are in physical sciences like physics, chemistry, and other things. Applied sciences like engineering, computational biology, applied statistics, mathematics, of course, in medical physics, and other fields like forecasting and in share marketing. There are so many places where applications of Monte Carlo are being used. Now we are going to specifically talk about the Monte Carlo in medical physics. MC codes are developed and used in medical physics for various purposes. For example, like you want to do a calculation, a shielding calculation, how much shielding is necessary. So that can be done by using MC. Design of linacs and instruments. Like you want to do I want to find out the detector. I want to find out the correction factor for the detector, how much it should be there. That also can be done by using a Monte Carlo codes. Dose distribution and treatment planning. And there are other applications of Monte Carlo in medical physics. There are various generalized codes are available. Like EGS is one of the generalized code, which is open source. It's an electron gamma shower. There are other codes like MCNP, Monte Carlo N particle, GN4, geometry and tracking, There are so many other codes available. There are many. These are some of the open source codes. Are some each are having their own type of licensing. Like EGS is the open source license. MCNP, the advantage of MCNP is that it can simulate a neutron interactions, whereas the EGS cannot do that. So we have a MCNP extended code which can do up to 34 different types of particles can be simulated in MCNP plus code. Gian4 can also do a neutron as well as pion proton simulation can be done in Gian4, whereas that is not again possible in EGSnrc. EGSnrc can only do simulation for photons and electrons, but that is what we need in our medical physics in our applications. The advantage of this is it comes with a number of user codes. Along with EGSnrc, when you download it, we get a lot of user codes which can be utilized or manipulated or modified to suit your purposes. And it has got some GUI, because the problem is nowadays we are used to GUI based softwares. So, but I will say that you will, once you get used to EGSnrc, it is better to use without a GUI. GUIs will always be hindering in your things. So we have some graphical user interface available for EGS also. That also I will deal it. Easy to do modeling for medical Linux like BeamNRC, that can be done. We also have a MC Monte Carlo based treatment planning systems available like Peregrine, VNC, VNC++, MC DOS, DPM, and MMCTP, which is specifically meant for your EGSnrc. That also actually we can deal later. Okay, so we'll deal first of all some theoretical part, that is Monte Carlo radiation transport. What is the radiation transport normally? So when we know that radiation enters a block of material, now when the radiation enters through a material, what will happen in that material now? That's what we are trying to do. How the interaction takes place, what the dose, how the doses are being deposited in different or energy or kerma or whatever you want to do it, that can be deposited. So for which we always have to do some sampling process. So for the probability distribution, there are various type of sampling process available. One is called uniform sampling, inverse transform sampling, stratified sampling, acceptance rejection sampling, and there are so many sampling methods available in probability distributions. We'll be using some of these transplant methods in our EGSnrc. I will tell you later. Now, we'll come to the complete step of Monte Carlo simulation now. First of all, what exactly I wanted to do in a Monte Carlo simulation? Let us say, for example, I want to create a phantom. I want to have a phantom created. Now, let us say I have a photon entering this phantom from here. Now, I know this is the point where it interacts. First of all, interaction. When the photon having certain energy interacts with this medium, how long it can travel without uninteracted in the medium. That is we call as a mean free path. Mean free path. So first of all, I had to find out that how long this photon can enter or pass through this medium without uninteracted. Let us say, for example, some x distance. I say that x distance is the thickness. It enters through the medium. After that, it starts interaction now. When this starts interaction at this point, what will be the type of interaction? So first of all, I should know the medium free. I should know the medium actually free path. Mean free path. Sorry, mean free path. That can be calculated. We know that mean free path can be given by the formula easily. We know that mean free path is given by the lambda, that is equal to 1 by mu, mean free path. Then after that, what I should know is now in the mean free path, after that, that is the average distance. But I want to know exactly what distance is going, because I'm going to sample it. So for that, I have to use a method called, now here, inverse transform. Like I told you here, inverse transform sampling is being done here at this point. At this point, inverse transform sampling is being done to find out exactly how much path it travels, how much distance it travels. That's the x distance. The mean free path is lambda, whereas I'm trying to find out what is the x. So once I find out, I sample it, I find out that then at this point, the interaction is going to happen now. Now, what type of interaction is going to happen? So that can be we have a coherent, we have an incoherent, we can have a photoelectric, and of course pair production can happen. Apart from that, we are not going to do any other things. So these four can happen. Now, what is the probability of each interaction? Again, we have to do a sampling method. The sampling method here used is acceptance rejection sampling here. So at this point, acceptance rejection sampling is done. At this point, the inverse transform sampling is being used to find out that. I'll show you actually an example of that in a Python code, how it is being done. Okay, I'll show you that just immediately after this. Okay, now I determined which interaction happens. The first of all I did was that I did a sample length. I decided the photon is being stopped by this x distance. Now whether I check it, whether the boundary is crossed, whether the boundary of this material is crossed or not. If it is crossed, I stop it. No, again I go to sampling method. Okay, now I find out all these four methods are the Rayleigh among the coherent. Rayleigh scatter is being important. So we have a four methods of interaction. Whether any of this, which four method of is being used, I have to do a sampling again here. Now that sampling decides which type of interaction happens. Based on that, I'll be using mathematical expressions. We know about that. We know when the photoelectric effect happens, the photon is completely lost. When the Compton happens, we know that some of the energy is transferred to the static photon, and the photon goes in a different direction. So we will be using at this point using a clean Nishina coefficient will be used here. Gas production, Rayleigh scattering also we can do it. So that is the method we are using it now. So once we decide which type of interaction happens, accordingly we have to deal with that one, and whether the photon goes here or electron, where the electron goes here, electron is happening here, that we have to deal separately. So at each and every plane, at each and every point, we can score it. We can find out how many photons are reaching that point, how many electrons are there, what is the energy of the scattered photon, that also can be found out. So this is a simple method of inverse transform method, in which I'll find out that first of all, the inverse transform method, x is equal to, x is already given here, x is equal to minus logarithm of r, which is a random number, divided by the mu. That means it's equal to lambda into minus logarithm of r. That is what is your distance traveled by the photon uninteracted. So here we use this method. This method is called inverse transform method, sampling method. Once it is decided that we have a Compton scattering, then we have to use a clean Nishina formula for interaction type to find out the angle of interaction, angle of a scattered photon, and the angle of the scattered electron which is released from that. So that both the things can be found out by using this, using clean Nishina formula. Clean Nishina formula, we know that actually all the physicists will know that about that. So we are using this relationship to find out what are the things. Again, this clean Nishina relationship cannot be estimated like this. We need to use another sampling method called acceptance rejection method, or we call simply rejection method, and that is what is being acceptance rejection sampling method is being used to find out that. Okay. Now, I have been telling that we have to sample it. We have to sampling it. The sampling method is being used again and again. I have been telling that. Now, I should now tell you something about random number generators. Why random number generators are very, very important in this Monte Carlo? Because every sampling involves random number generators. Without random number generators, RNGs, we cannot have any stochastic process happening there. Okay. Many of the most useful Monte Carlo techniques rely on deterministic pseudo random number sequences. Ideally, we need two random number generators. We need two random numbers because we know that a two random number generator is very difficult to get. Like example, a two random number generator is like your decay of a radioactive isotope, which is a two random number. So we can't. No one can predict which atom will be decaying at that any particular time. So that is a two random numbers. But in a mathematical or in a computational method, getting a two random number generator is very, very difficult. So it's not possible. So we normally use a pseudo random number sequences. We use it. Okay. But only problem is that what is the quality of the pseudo random sequence that we have to ascertain first of all. What is the quality? Whether we are able to get a true random or is it something nearing the true random sequence, that we have to find out. For a random number generator, we need to have a certain methods. Like what we do, we give a seed. The seed is taken as a random number generator. It uses some mathematical functions to estimate a random number 1. Then that is used as a second seed. And that is again a random number generator, again uses the same mathematical expression to find the random number 2. And this goes here again as a seed here. And this process repeats. So that means that we can create many number of random sequences. There are many methods of pseudo random number generators. Simplest method is we know that random number generators. Once we talk about random number generation, immediately comes to our mind is estimation of pi. Estimation of pi can be found out by using MC codes or Force needles problem, that we drop a needle and within the circle how many are falling, and without the outside the circle how many are falling. Like here the sticks, which is crossing the, like here it's crossing it. Suppose something is not crossing, it is crossing it, then that can be found out. And many methods are available in random number generators. Excel's inbuilt random function, Python's random module, and NumPy's rand module is also available. I will discuss something about the LCG, which is a linear congruential generator, just to tell you the importance of true random number generators. What is the importance of that? There are other random number generators like RANMER, RAN-ECU, RAN-LUX, and RAN-LUX++. In EGS, RAN-LUX++ and RAN-LUX, these are two common generators used in random number generators used in EGSnrc. I'll tell you the importance of that also. I'll tell you now. Okay. So, okay, I want to just go out of this PPT now just to show you how the random number generators are important here now. Okay, so now I have an Excel sheet here. So here I put up already, this is the LCG. This uses the LCG method. That is a linear congruential generator. I've generated actually around 100. I think it is 200 random numbers are generated here. Okay. This LCG method requires certain inputs. One is a seed. A is another one you need. C is the multiplier. And of course, another important thing we need is a modulus. Every random number generator, the modulus is very important. The modulus here is something called a 2 power. It is called a 2 power. So the random number here requires that I have to give a value in the order of 2 power m or 2 power x, you can say, whatever it is. So that 2 power x becomes my modulus of this material. Now here I given my x is 4 here, I'm getting 16 here, just to show you that you can see from this is my seed. The seed value is 27. I given a seed value of 27 here. Now you can see that 16 is my modulus. It means that after 16 values, it starts repeating the random number generators again. You can see that the values are being repeated here. So whatever you are seeing here, of course, leaving the seed value, these values will be repeated here again. It means that is not a true random number generator. So what I can do is now, suppose I say that if I increase this value now, suppose I increase this value to, let us say for example 16. The value obtained is so much. You can see the values, and you can see that the numbers are not normally not repeated, but it will be repeated again. But you can't see that from here. After 65,536 values, the number will be repeated again. So we are trying to get a near true random number generators. So using the two pseudo random number generator values. So it means that my modulus, the 2 power value should be very, very high. And that is what is being done in this. That is in RANLUX. Normally, they say that in RANLUX, the value is available is something around 2 power 24 is normally used in RANLUX, and RANLUX++ is 2 power 384 is being used. 384. It means you can just imagine 2 power 384 will be such a huge number. It means that we can imagine that the number is not repeated. After many numbers only be repeated. This is the formula for LCG. It's the formula for LCG. What you are seeing is the formula for LCG, that what I use for in Excel sheet. So in fact nowadays they say that in fact nowadays RANLUX+ it can go up to 584 also. It can go up to 584. Such a large actually random number generators are being used nowadays. So we are trying to reach near to random number generators. So random number generation is a very, very crucial part of every stochastic sampling method. Okay, so this is what the method I use. Actually, I already told you about seed is used. seed is being put in the second seed. Okay. Now we'll go. So now we know about the importance of random number generators. So we'll be using random number generators at every point of time, because even at here also, at this process we need a random number. This is a random number generator is being done here. We use a random number generator here, and even in this process also we will be using random number generators to find out or the estimate which process is taking place. Now we find out a RNG. The RNG value is less than a certain value, then I will say that we have a coherent happening. If it is less than and greater than a certain value, I would say that photoelectric effect is happening. If it is less than again another certain value, I can say incoherent is happening. Same way, if it is greater than some value, I can say pair production is happening. That's how we estimate which interaction takes place. I'll show you an example of that again, how that is taking place now using a Python code now. So I have a Python code now here. We have a Python code that you can see from here in the screen. So this is just to find out the mean free path and the estimate which type of interaction is going to take place now. I used random number generators again. Inbuilt NumPy random number generators being used in the Python code. Okay, that find out the. Now I want to find out. I can do it for any material for that matter, because I have given a certain values. Like for water, I given the value. I'll tell you about what is the XCOM value and the rho values and what I'll tell you later. But I given that I'm estimating it for the lead now. Now I want to find out what is the random number generator, how they are used. Now I'm going to run the code. Now you can see from the screen that I've done for 10. The first time the length of travel is 10 centimeters. Then the next one, length of travel is 202 centimeters, 34 centimeters, 70 centimeters, 723, and you can see that this is what length of. This is what you are getting it now here. And the type of interaction, what is assumed or what has been sampled is, first one is Compton, coherent, Compton. So we can see that from out of this 10 interaction, what the energy of the Compton coming out is this. Okay, that's also given. And directional coordinates also given. So it means that I can find out the directional coordinate. I can find out using, here I used a Klein-Nishina formula. So we use a Klein-Nishina method. So we use a Klein-Nishina weightage and to find out the theta value. That means that angle of actually interaction about the deposit energy. It's giving deposit energy also. So this is a simple method we can find out just only for one, actually a 10 photon history. We have find out that. Same way I can repeat this for many number of photon history. We can get that value also. You can get it. Now we'll go get into the after this physics part and Monte Carlo part. Generally, we will now get into the EGSnrc. What is EGSnrc? We know that EGSnrc is a Monte Carlo code. It's a free open source code available, and it got a lot of very extensive actually documentation is available for this EGSnrc code. So anybody can download, install, and configure this as per your system. Now, I want to have one more disclaimer is that I have never installed it in Windows. I always install it. My system is running Linux, so I always install it in Linux. I also have a MacBook. I installed in MacBook also. Both are running perfectly fine. I never installed it in Windows, so I don't know actually exactly what type of problems people face it. And among this EGSnrc, you choose a code for usage. So what we do is now. So Dinesh, is it? Can we stop and go for the use?
Yes, sir. I think there is some connectivity issue with your network or somewhere, sir.
Okay.
Your voice is somehow breaking, which is fine. Yes, sir.
Should
I
we
will
stop
go
or
for
should we continue that now?
We'll continue, sir. We'll continue. The flow
Okay,
is
no
good,
problem.
right?
Okay, then
We'll
okay.
continue as it is.
So first thing is for EGSnrc, you have to download, install, and configure. Then there are various codes available. So we have to choose the code for usage, which code you want to use it. Then create and modify the input file, create select density file and PEX data file, compile the code, execute and run the code, and read and analyze the output file. We'll see one after another. First thing is download. EGSnrc is a NRC means National Research Council. So which is the electron gamma shower and devised by the National Research Council Canada, and it's the URL for EGSnrc is given here. It's easily downloadable from the Git repository. You can download or you can clone it. Both you can do it. EGSnrc is basically a set of source files. It's an open source. I told you that it's a source file, and utility is to build your own Monte Carlo simulations. EGSnrc was developed using Motron, which is nothing but a photon, which is the More photon, C, C++, LaTeX for documentation, TCL/TK for the GUI, and of course some shell scripts are there. So naturally, to run and compile and run it, we need Fortran compiler, C compiler, C++ compilers we need. Make utility, GNU make utility is needed to make or compile it. TCL/TK for GUI toolkit. Grace for graphically displaying the output. As I told you, I have installed EGSnrc in Linux many times, so many times, without any issues. For Linux, EGSnrc gives a native support, no issue at all. It can be easily installed. It can be downloaded from the installation instructions are given in this URL. We can go to this URL, install EGSnrc on Linux. It will give the instructions, step-by-step instructions given there. Easily can be installed in Linux. For MacBook people, you can install EGSnrc. I have done it. Actually, it is working. Using Homebrew, we can install instructions again given in this page. For Windows, I never installed actually Windows, but instructions are available in this page. I have seen that in the forums, I have seen that people have used MinGW or Cygwin. They used to compile the code using the MinGW or Cygwin. They used it. That's what I know. I never, but now done. Of course, actually we can do like virtualization softwares, because those who are running Windows, they don't want to shift to Linux. So what they can do is they can do a virtualization software like VirtualBox or Docker or any other things. You can use it to install the Linux, and from the Linux we can run it. I have done it in a Raspberry Pi, which is a very small. Actually, we know that maybe many people may be knowing it. This is a Linux. This is a Raspberry Pi system, very small single board computer, simple computer, and the main advantage of Linux Raspberry is it is useful for automation and clustering. I have done, this is my own actually cluster. This is using four Raspberry Pis. There are four Raspberry Pis are put in a cluster, and we can do automation using these clusters. And I have run it. It's working properly. With this, like I can keep on building up many actually Raspberry Pis. We can run them parallelly, because we know that we'll be seeing later also that every EGSnrc simulation requires millions or sometimes billions of histories to be simulated, which is not possible by using a simple systems. We need to have parallel systems to be run. So we can use the Raspberry, like these clusters can be developed or can be done. So what is the EGSnrc code? We choose a code first of all. Which code you want to do it? There are a lot of codes available. We'll see after this. So we input an input file. We have to create an input file, which has the controls for source, dimensions, materials, etc. will be there. And we also create a material data, like we have to have what type of material is going to be there. Is it going to be a complex material, geometry, what type of geometry is going to be, and all the things will be put in this specs4 file. That will be there. This is the structure of layout of EGSnrc, where there are a lot of codes are being done here. We can deal it actually when we are dealing in future sessions. As soon as you install EGSnrc, there will be it will ask you when you're doing that one. It will ask you whether you want to compile the GUI also. You can say yes, and you can compile it. Once the installation is complete, we'll have the 6 icons put in your desktop. Each one represents different one. Like we have a EGS GUI, dose XYZ NRC GUI, beam DP GUI, EGS input RZ, EGS view, beam NRC GUI. There are many command line based codes available which is not having any GUI based systems like stat dose, CT create, examine, G, read face, beam build, dose XYZ show. I will show you some of the things later. Randmer test, Randlex test, EGS Kerma, EGS CBCT, tutor codes, and so many other codes. Of course, latest one is EGS++. I will show you some of the GUIs here. First of all, we will go through that also later on. And we have, this is the basic layout of a EGS GUI. Here, this is useful for doing some basic operations like creating a PEX4 data file, compiling some user codes can be done using this. This is a GUI for input RZ. This is RZ geometry. This I'll be opening it up lively. I'll show you a demo of this one also later on. This is a dose XYZ NRC. This also show you. This is a beam NRC GUI, beam DP GUI, and EGS view GUI. Once we actually install it, it will have two folders. One is the hen house. Basically, EGS is called X. We can say X NRC. So we know we can now I can understand the X is mean coming from the hen house. That's why they put a folder. This is the folder they have called hen house because it's X folder. Okay, so X are hatched here. So it's called hen house folder. This is the basic core folder where EGS will be lying. And we have to create our own configuration folder for the user, which is called EGS home folder, where I'll be putting my own files. So that's called EGS home folder. This is a X folder. This is a hen house folder containing many files, and EGS home folder also containing a user created. These are some user created folders. I created many of the files here. Some of the files are created by me, so they have this. Okay. And next is we have a documentation. As I told you, that extensive documentation available for EGS NRC. So each are available there. And EGS NRC is the hen house folder contains a folder called PEX4. You can see from there's a PEX4 folder. PEX is nothing but a preprocessor for EGS X. Preprocessor for EGS called PEX4 folder. And there are user codes available. There are many user codes available. So first of all, we'll deal with the geometry definitions. I want to deal with RZ geometry, some part of XYZ geometry, and some complex geometry using EGS++. RZ geometry is best suited for obtaining data for central axis depth row curves. It has got many sample codes like dose RZ, fluence RZ, stopping power ratio RZ, cavity RZ. The RZ geometry, name is RZ, means that it assumes that your phantom is cylindrically symmetric phantom. We have a cylindrically symmetric phantom, like we have a radius Z values. That's why it's called RZ. RZ here means one is a radius, one is called radius, other is called as Z value, that is depth values. So we have radius values. So assuming that we have a cylindrical phantom having various depths, I can divide them into various depths. I have a slabs of cylinders available there. And I can assign different medium for different points here. I can assign it. I can define into this. I'll show you an example of this now. I want to show an example of the RZ geometry in the live one. Like this is my RZ folder. And remember that every code of EGSnrc can be run from the GUI also, as well as from the terminal or the command line also. So I may be using sometimes command line, sometimes GUI. For first session, first thing I want to use a GUI and show you that. So you can see that this is the RZ geometry, GUI. This is the GUI for RZ geometry. I already told you about the 4 codes available here. We will deal with those RZ. When you open this GUI, it starts with this window. There are so many actually tabulated tabs available here. We can go through the tabs here. There are so many tabs available here. And they are also given many templates are given. So I am using the template here. So I'll be using this template called those RZ NRC template. I'll be using this. This template defines the input file, because see, you can see this from here. First of all, every EGS NRC code requires 2 things. One is the input file, it's called PEX4 file, PEX4 data file. So here, the first thing is input file. If I click it here, I'm seeing this user code area. This is defined to this, related to this. I'm telling that the user input file should be taken from the EGS home file, not from henhouse. You can have any other folder also. I just click it, it will open up a folder. It's asking me to open which one you want to open it. I already put it here, so it's opening from here. Whereas PEX4 data file, I given a default values from henhouse folder, so it is giving a henhouse folder here. Again, I can open it up. I can go for any other value also. I can go for any other file also, but I'm just sticking to this now, right now. Here. Now, what I'm going to do is now I'm going to just go through each and everything here. Now, as soon as I load a input file, it is giving me the geometry. I'll go to geometry first. Here we have defined a geometry. This is the plane. This is the plane that is Z value. This is R value. Z and R value. That's the RZ geometry. I have given a material having different radiuses. Same way, having 2 different slabs. I'll show you this also. We have something called a preview RZ. I want to see whether I've done the right thing or not here, that I can do it by preview RZ. I click it here, it shows a window. This what I put it here. The radius, the radiuses. The values, Z values up to 10, then up to 50 is here. So I given that also. So now, since you are not able to see this, I'm going to show you a little higher level resolution. Okay, now I'm going to put it here. I can that also you can do it. Now you can see this here. Now again, I'm not possible. So what I'm going to do is now, I'm going to put it here now. Now you can see that the preview window is enlarged now. What you can see from here is, now you can represent this. This is the first radius. 1 centimeter is the radius 1. Then 2 centimeters is radius 2. 5 centimeters radius 3. Then 10 centimeter radius 4. The remaining all are single radius. Same here for plane. 10 planes, Z value of 10 means that I'm telling the system that each 10 slab, first 10 slab will have a 1 centimeter thickness. You can see that first 10 slab is having 1 centimeter thickness. Next, I'm telling that 50 slabs will have a 2 centimeter thickness. Next 50 slabs will be having a 2 centimeter thickness. Means that 100 and I have a thickness of, this is 1. It means that I have a 110 slabs will be the total. This is 100, this is 10. So 110 slabs will be there here. What I'm saying is 61. Okay. Now that's what I defined the geometry. Now I'm telling the material, what material it's made of. First of all, I'm telling that all the starting from first to all are made of water. I'm telling that the whole thing is made of water. That's a red is given. Red is for water. I given it here. I can also change the colors. You can change the colors also. That's great. Okay. Now, but I'm going to define a air cavity within this RZ geometry, and that is a very small air cavity here. That will be starting from the Z value of 11 after 10 11th value and stopping at 11. It means that only 1 pixel value. That means that only 1 small content here. And starting from radius 1 to the same radius 1, it means that only a smaller part of this is your air cavity. Now you can clearly see that one. So it means that I defined the geometry, I defined the material for that. Now next is I want to define the input output controls. That will not deal it later. It's that we can, because it's a very important thing is Monte Carlo next. Now I want to go for the, as we know that it's a stochastic process, I need to the more number of histories, more accurate it will be. The variance or the difference will be, a standard deviation will be very low. So I have to have a large number of histories to be simulated. Or I should now tell you that more number of estimates, naturally more number of CPU hours. That's the reason I told you a parallel session means number of cores we have, then I can parallelize it. That will be better easily. So here I given you some actually number of cores or number of histories are given here. Now I'm going to define the source. What type of source is going to be? I'm going to simulate a photon. And whereas there are so many number of sources are given. A source in the sense that how the beam is going to be directed. It says that source number 0 is parallel beam incident from the front side. Same way, if I say other one, central axis fluids. If I go to 21, actually normally 12 is another one. Point source. There are numbers are given there. 21 is again another one, phase-based data. So there are number of sources available here that you can work around. Now I'm going to stick with this 0. Then transport parameters, there are many algorithms available. We have I told you again about sampling. Here we have to talk about the sampling methods again. Already they have EGSnrc got many codes available, Presta code, which is algorithm, and we will not deal with here now, right now. And various reductions to come, and plot control, how to plot it, that also can be. Now I'm going to run it. How to run it? I can run it from the GUI as well as from the terminal. Now I'm going to execute it and compile it now. I've got already compiled, so I'm going to execute it now. Now I'm going to run it. You can see that here it is running. It is running. In batch by batch, it's running. We are given a large number of histories, so it is running. Now it's over now. Now it's over. It says that interaction run completed. Suppose I say that here I'm going to do a still more. I'm going to add one more 0. I'm going to save it. Yes. Okay. Now I'm going to compile it. Sorry. I'm going to execute this, run it. Now you can see that it takes longer time. It takes a longer time because I given one more another 0 is added here, so it's taking a very long time. I can now second batch is running. Likewise, all the 10 batches will be running. After 10 batches, it will come out with the result. Now we will go and see the result, analyzing the result. I'll kill the process now. Okay, I'll kill the process and I just reduce that one. I'm going to save it again. Yes, I'm going to execute it. Now it is over. Now reduce number of histories, so it will complete it fast and over now. Now I'll go to the directory and show you how it is happening now. Now you can see this. What we saw was those are the templates. When you run it, this is the input file. It creates so many other files. It creates. We can see this. I can open this with another application. I can see the input file. See, the input file is again a text file. I can see the input file also. Here I can see that I can tell you this number of histories are there. Everything is available here. I can even modify this file directly. Instead of going to GUI, I can do the thing directly also from here. See here, suppose I want to change the number of, what is the medium, how many number of histories I want to see. I can change the number of history here also. I can do it. That everything can be done here. So those are that generates important file. One file is DD file, that is depth rows. I'm going to see this file using the GRACE, which is the graphical user interface needed for EGS. I'm going to show this one here now. You can see the depth rows curve. This is a water cobalt beam. This is a depth rows curve. You can see the depth rows curve. What you are seeing this is the variance or the errors. The variance or the errors. This variance or the error can be reduced by increasing the number of histories. That by increasing the number of history, I can actually reduce it. That can be done. That's about your EGSnrc, RZ-NRC. So now I want to quit this RZ-NRC. Move on to this again. So this contains actually again, we have a X4 data file is the material data file. What happens is here, Now PEX is nothing but PEX is a preprocessor for EGS. The data file needs, the material file needs the data. What data is needed here now? That's important now. What data are needed for that? We need to have the data about the interaction coefficients. Like we have a linear attenuation coefficients, mass attenuation coefficients, and the mean ionization energy, stopping power ratios. All the data are necessary already inbuilt in EGSnrc. If you want to develop your own, like what I showed you the Python code, if you want to develop your own code, we can download the data from these things like NIST, National Institute of Standards and Technology. They have a web-based XCOM database available for photons. They have a for up to atomic number of less than or equal to 100. We have up to 100 atomic number elements are available there. For some compounds like water, soft tissue, they are also having that. It covers 1 kilo electron volt to 100 giga electron volt. And all the data is available. This data can be downloaded and we can use this for your own code if you want to do it. You want to develop your own code. This is the URL for that. For electrons, protons, and alpha particles, NIST again provides a different code, different databases. They call E star, P star, and A star, which is useful for calculating the stopping powers, range, and other related quantities for these three particles. Again, it's available for 1 keV to 10 GeV. Databases are available at different points. One of the examples is estar.html here. Same, you can put pstar.html, astar.html, get the data available for this. So those data are already incorporated in your PEX data file. Here, PEX file contains this. This is a PEX file here, one of the sample PEX file here, which like example here is AR521 ICRU. That's what I'm using it. We have density files available for various elements, and input files are also available. PEX for. So one of the example I showed you was RZ geometry, and I want to show you one of the example of using XYZ geometry. I will go to XYZ geometry. This is the XYZ geometry GUI. So once you open it, it will be like this. So this is a very simple interface. It looks like a very simple interface, but very complicated interface. In fact, it is the beginning. You have to either create your own input file, new create, or you can load, which is already done. Suppose you already saved an input file, that you can load it. So we have to load a previous input file. I'm going to load a file called my phantom EGS input file. Okay, I'm going to load the PEX4 data file, that is a 521 ICRU PEX4 data file. I'm going to load it here. Once I load it, I say that these two are going to be used for this. Okay. Suppose you want to edit this file, you can edit it as well. You can do that also, because I can define the X, Y, Z, X, Y, Z. You can do all the things can be done. Media can be defined. I can define any media, whichever voxel I want to do it, I can do it. X, Y, Z takes care of the three-dimensional voxel geometry. RZ is a cylindrical geometry, whereas X, Y, Z is a voxel geometry. Biggest advantage of X, Y, Z is I can even have a load a CT data phantom here. CT phantom can be loaded here. That we'll deal later. That beam NRC along with the XYZ geometry, we can do that. We can put a data on a CT data. CT data can be converted to CT create, and it can be loaded here. That can be put here. And again, we have to have a number of histories. That everything is available here. I can close it now. I want to run it now. I have already compiled this code. I'm going to run it now. Now, once I execute it, it will be run. It is running now. Same way, 1, 2, 3, it is running. Batch by batch, it is running. Done. Job is finished. Now, I can close it. But what is the output now? I want to check the output now. I'm going to show you the output now, output file here in the EGS XYZ NRC. I showed you was the EGS phantom. Again, EGS phantom, this is the input file. We have input file available, and we have a 3D. These are created files. EGS phantom file, EGS 3D dose files, they are created now. I want to see what exactly it outputs, for which I'll be using again a code, but not directly visible from here, but it has got a GUI that's called dose XYZ show. This is how you have to open that one. I'm going to open that file. Okay, I'll just check. Okay, something is not working now. Okay, the output of this will be like this. I can show you that now. The output of that will be looking like this. We can see from that actually what this is the depth rows again. Some of the outputs actually I obtained here is using this. You can see this is your isoros, sorry, profiles. You can also get isoros from here. So we can also get other things like this is actually a beam source. Actually, we use it, but we can see that the variance is very actually low. It means that it is done for a very long, actually more than a million, actually 10 million simulation it has been done. Okay. At the end of that, actually, I want to show you some examples on the EGS plus plus, because EGS plus plus is nowadays coming up in a very big way, because uh, some of this is actually useful for beam NRC is useful for actually Linac head. Okay, and dose XYZ is useful for a phantom, a voxel phantom. But when you want to construct a chamber or any other thing in complex geometry, EGS plus 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 is useful. Now I will show you some of the things in EGS plus plus, how that will be useful. So I want to show you one example using EGS plus plus. That is, I have created a uh, one actually app I created here. I compiled it already. I want to show you that means that we have created a slab phantom. I created a slab phantom. On the slab phantom, I want to apply a source and find out the depth, how the radiation is being scattered or what is happening inside that. So I'll be using a slab phantom. This is my input file. This is my input file. Every EGS plus plus needs a certain actually sort of a geometry needed here. Certain sort of a structure syntax is required from here. I created a structure already. Now we can run the things and we can see that also output of that one. Using another actually code available in this one, EGS view. I have actually already compiled it. You can see from here that this is the EGS++ geometry. I have created a geometry here. We can three-dimensional, you can move it and you can rotate and see that also. And this consists of a water phantom having a tantalum inside. This is a sample code given in the actually the document also. But we can create anything. Actually, I created many other geometry also in this. I can show you that. We can just change the transparency of this. You can shift it and you can see that one. Now water phantom has been actually given a transparent medium. I have a tantalum is given a full actually one. Tantalum is having a full opaque one. I can see that also that which one you want to display. You can see from this the red ones are the electrons. If you click it here, electrons are gone now. It means that radiation source is entering from here, radiation is entering from the point source, and it's getting scattered. And this is a there is no positons. Of course, there are only one, very few. This is the photons are there. If I want to see only the electrons, I can see the electron only. Photon, I can see the photons also. So that way, EGS++ will help us in designing various type of geometry, because that is a full-fledged. You can write your own script, and you can actually apply it on this, and you can see the how it is coming up. You can see that also. That's all. Actually, I want to just I want to show you some of the things which is obtained from codes. 1 mm photons, 10 mm photons. You can see HUL measurement. This is what actually that EGS view I was trying to show you the dose XYZ show. The output looks like this one. Excitement. The other day also I saw it was coming. This is how the profile comes up. You can see the depth rows. You can see the iso-roses. We can change the colors. We can change we want. The dose XYZ show gives you this window. This is what my actually app I showed you that already. I have this also. My actually we can put different phantoms and different slabs, different materials. I can analyze that. This is a beam NRC where we can define the or design the LINAC head. Thank you. Any questions you can just ask. Mr. Dinesh?
Yes, sir.
I completed now. Anybody?
Yes, you can have any questions we can ask now, the Q&A time.
Yes, sir.
You can unmute your mic, you can speak, or you can drop the question in the chat box also.
Can you hear me?
Yes.
Hi,
Yes.
sir. This is Satish. Good to see
Okay.
you after a long time. I have a question about. Good, sir. Good, sir. I have a question about this. The Raspberry Pi you created. Do you have any GPU installed or a simple RAM?
This is okay. See, this is only a simple RAM only. No GPU in this. There's no GPU.
Yeah, I have a Raspberry Pi. Usually, I have even work with it a lot. But I don't know whether we need a GPU or just a RAM.
No, actually, the problem is no. This is having the same RAM, 8 GB RAM. Okay, but by putting the number of actually, you make a clusters. If you make a cluster, then what happens is all the jobs, like the job scheduling will be done. The number of the histories will be divided into number of jobs. So that will go to individually. At the end of the job completion, everything will be compiled. Everything will be combined together and give you the final data. The final result will be
nice. Okay, it's like a shared core.
Yeah, it's a shared core. Basically, actually, that's what I want to say is, RAM is needed only when you want to have a complex geometry. When you have a very complex geometry, then higher RAM is okay. Because number of voxels, they have to store the data, so RAM is okay. But for doing a large number of histories, RAM is not important. Number of core is important.
Nice. Okay, sir.
Okay.
Thank you.
For example, let us say you have a system with something around 12 cores or 16 cores. Then suppose you don't have a normal system comes with 4 cores. So what we have to do is now we have to divide it to 4 cores only.
Nice. Okay. Got it. Thank you, sir.
Any other? If there is no question, then. Okay, I am seeing one actually question in the chat box. Okay, actually, since I'm not this session actually will not be able to cover the beam NRC. I understand that beam NRC along with the XYZ, those XYZ geometry will be a very complicated topic, and it needs a full session for that because we have to see how to design the head of the LINAC. In fact, actually, I can show you some of the things I have done actually for variant LINAC, and I think I have available. But the problem is I'll not be able to cover it now right now because it's a very huge topic. Okay, so you want to create your own phase-space data. So you do have a okay. So the variant has given you the phase-space data. We can do that because by feeding, because in fact, IAE has given various phase-space data available in the net. Internet is available. IAE phase-space data is available. That also you can take it out and you can actually work on that. Suppose a company data is already available, variant data is already available. That also you can input as a phase-space data in those XYZ NRC, and you can design your own phantom. Then you can find out those profile can be found out. That can be done. I showed you that window. Like actually, when you go to the window, like here in this window now. Now I have to actually input the phantom non-city data input. We can put that anything actually. We can put it here, and in fact I can use the incident particle, what type of source you wanted. Here we have a phase space also available here. Phase space source is available here. You can see this. At the source number 20 is phase space source through dynamic library with the multiple variable geometry settings. That also you can utilize this multiple directions. So that is one of, so you have to choose one of this as a source. Then you have to put your phase space data here. So phase space input has to be put here, which is the file you are using it. The current direct phase space file you have to choose it. Like I am putting Eldorado here. Actually, we have so many other things also available. I can use this as a file. Okay, so then we can compile it and we can run it. That can be done.
Thank you, sir. Any more questions from our participants? We'll wait for 2 more minutes, then we'll wind up the session. If any more questions, then please ask. Okay. You can drop it in chat box also if you have any questions. Fine then. And to Dr. Bilal sir, really thank you for such an interesting and informative talk. What do you say? Like this presentation helped us understand the concept of very in a both theoretical and practical way. Actually, we've seen exact like how you have performed that, and really thank you for sharing this your experience with us, and we are really grateful for that.
Thank you so much, Mr. Dinesh
Thanks.
and other participants for giving the valuable time. Of course, this is a primer. This is basically a primer on the Monte Carlo. So I know that actually many things could not be covered in this one. So we can actually that can be covered later on. Actually, there is any future sessions, and because each actually code requires a separate type of, because the installation itself is a little typical. And we need to actually work on the installation part, because some people have faced a lot of problems. I also faced, initially I faced some problems. And later on, actually, now it has become easy to install it in Linux. I become very easy actually to put in Linux. Now, what happens is when you do it in a different actually installation configurations and different type of codes, then each one needs a separate actually inputs, because what type of input we need, what type of phase space. In fact, I could not cover the how the PEX4 data file is being created. That also can be covered in a separate session. We have to have we how to take the density file, what is the density file, how to take the density file, how to convert into a PEX4 data file. So there are, it's a complete actually, we need to have a full actually complete something around 1 week session so that we can cover the whole thing. Somehow I tried to justify within the short time I'm able to do it. I think anybody could actually comment on this. Anybody have any comment on the whole all over session, feedback on the session, you can also give it to me.
Yes, sir. And this session is only a tip of the iceberg.
Yeah, of course.
Of course. There is one more question, one last question, Mr. Subhajit Maitra has been shared, and then we'll wind up.
Okay, I'm also. Okay, I can see that. Okay. So what actually is he here online now? Subhajit Mitra? Can you unmute actually? And,
No, he's in the chat box.
okay, he's not.
Hello.
Yeah. Yeah. What is exactly your problem actually? You are using a dose XYZ NRC?
Am I audible?
Yeah, of course. No.
So actually, in being I try to make a field size dependent test case data, but it is showing some kind of error like geometry is not properly defined that kind of.
You have created a phase space file now.
No, I have a phase space file given by variant, and now I want to create a phase space file for a 10x10 field size data.
Okay, you are opening a beam NRC and doing it. Okay, okay.
Yes.
Okay. What type of actually? Have you compiled the beam NRC?
Yes, sir.
You compiled it properly?
Yes, sir.
Did it show any error while compilation?
No.
No, no error while compilation. Okay. Did you actually, one thing I want to know is now, were you able to open any other phase space file in a beam NRC? Like IAEA phase space file? You are able to open it?
That I didn't try, sir.
Okay, what you do is now, I'll tell you the simple one is download the IAEA phase space file first.
Okay, sir.
Okay, then you try that. If that works for if there is any problem, then there is a problem with your beam NRC installation. If that works fine, it should also work. Otherwise, it's a problem with the phase space file provided by the variant. Because IAEA phase space file is found to be working with the EGSnrc perfectly. So I would recommend that first you use IAEA phase space file. Then try with that. If that completes actually successfully, then you can come to this one. That will be better.
Okay. Thank you. I will try.
And thank you, sir. And then thank you for the question also. We'll wind up the session as of now, sir.
Thank you. Thank you so much. Thank you all the participants.
Thank you. Thank you.